Because yesterday we changed from SECALEC to Institute, so it's the first seminar, the new institute. And to be presented by Birgit Lange and Birgit Lange, sorry, that's the pronunciation. And they are here because we are making a proposal between the University of Lübek and UNAM related with tomography, biological tissues, optical and acoustic characterization of biological tissues. And this is an extraordinary seminar because we're not planning to have a seminar today. So thank you for coming, and please.
Yeah, thank you very much for the opportunity to present our work in this seminar. So, my name is Birgit Lange, and where do we come from? We come from the northern part of Germany, from Lübeck. This is a small city with about 200,000 inhabitants near the Baltic Sea, near Hamburg. So there's a lot of water around the city and also in the city. You see part of the city, the historic city center, the Holstentor, and there's also a famous sweet coming from Lübeck, which is called Marzipan, which is made from almonds, so I brought some with me. And in Lübeck, there is a university which was founded in 1964 as a medical faculty of another university. So its strong focus is related to biology and medicine. And nowadays there are 4,300 students, so it's about 2 orders of magnitude smaller than UNAM. But there are also other research institutions on the campus and a very big university hospital. And together we are forming what is called the Biomedical Technical Science Campus in Lübeck. So our institution was founded in 1986 as a small non-profit research and development institute. And in 2005 there was a change, so the public funding then went into the newly founded Institute of Biomedical Optics, which is focusing on education and research, teaching, and also on basic research in biophotonics, more or less. The Medical Laser Center still continues, but without public support, so we are really strictly project funded by publicly funded projects, or also by projects which get financed by companies. So there's a strong interconnection between these two, and maybe let's say here is more the engineering part and the applied part, where here is more the basic research part. But in the Institute of Biomedical Optics, the director is Alfred Vogel. He's working mainly on nonlinear laser-tissue interaction, the interaction of pulsed laser radiation, nonlinear absorption. And then there is a strong, or there are several groups working on research and in vivo evaluation of new imaging modalities like optical coherence tomography. So Helge is giving his talk on this topic later, but also, of course, photoacoustic tomography, the work we were talking about on the last days. And there's also intravital multiphoton microscopy, and a group which is led by a biologist, Ramtin Rahmanzadeh. He's doing photodynamic therapy, and he's working also on photoactive nanoparticles and protein inactivation. I'll show an example later. Another field we are working on is feedback-controlled laser therapy. So, for example, if you coagulate the retina by laser, then you may want to know what you're doing and what the temperature actually is. So, this is another field, but also in other laser therapies, we sought for ways how to control this and make this somehow smarter. Last but not least, there's a small group working on laser material processing, so we are not only focusing on tissue, but also we are working with materials like glass or other polymers. As you can see here, for the Medical Laser Center, the CEO is Ralf Brinkmann, and he's also a group leader at the Institute of Biomedical Optics, so you really can't separate them completely. But here at the Medical Laser Center, this is more a mixed team of engineers and physicists, and we come into play mostly when things are translated into the clinics and when clinical studies are going to take place. The shareholders are the university and the university clinics on one hand, but also some companies which are working in the medical field. I'll give some examples of the work we are doing. These are I just selected some of them because otherwise it would take too much time. And like I already mentioned, I skipped the OCT part because Helge is covering this later. So in the group of our director, Alfred Vogel, he's really on the experimental and theoretical side, investigating how lasers are interacting with tissue, for example, how optical breakdown in dielectric media is taking place. So if you see here, if you focus a pulsed laser beam into, for example, water and have a high enough pulse energy, what's happening is a plasma is formed, a shock wave will build, and a cavitation bubble will start to expand. This effect you can, for example, use for nanocell, for cell surgery, or to cut, for example, a flap in the cornea for cataract surgery. This is just one example. But what you should know in this case, of course, how big is the bubble that is going to form. Optimally, you would want to really know reproducibly how big this is going to be. And what they did, they really did extensive research and used several laser wavelengths in the infrared and visible with different pulse durations from femtoseconds to nanoseconds, and did high-speed photography experiments to determine what the bubble size is when you use certain pulse parameters. Pulse energy is here on the x-axis, and then with different wavelengths and pulse durations you get a certain bubble radius in a reproducible way. So you can really determine what should the bubble look like. Okay, I have to take this or that laser parameters. In the nanosecond regime, you see here that this is only starting at a bubble radius above 10 micrometer. So actually, one person thought that in this regime you can't use nanosecond lasers because they don't lead to reproducible bubble sizes. However, in the Vogel group, they found that this is actually due to the pulse profile, the temporal pulse profile of the laser, because usually those nanosecond lasers, they don't run single longitudinal mode, and then you end up with a pulse shape looking like this, and then you can't get a nice bubble radius. However, if you use microchip lasers, which have a very small resonator length, then you get a nice temporal pulse shape, and then very smooth, and then you can also get here in a very determined way certain bubble radius which are below 10 micrometers. And of course, those nanosecond lasers are much cheaper than femtosecond lasers, so this is really a huge advantage. And they had also cooperation with a company which is now using nanosecond lasers instead of femtosecond lasers to do this flap cutting in cataract surgery. So, complete change of topic. In the biologist group, he's working on a very selective way to kill cancer cells. So what you have in cancer cells, or in most of them, is that you have typical proteins which are overexpressed in proliferating cells. For example, this Ki67 protein here in the cell nucleus, but also an epidermal growth factor receptor here on the cell membrane. And what they are doing now is they try to get an antibody for this protein into the cells, and they put them into a liposome structure and attach antibodies to this liposome structure, which selectively binds to this epidermal growth factor receptor. So this is the one selection step. Then this enters the cell, and they have here added a photoactive dye, and when they excite this with the correct wavelengths, then the liposome membrane will break up, and these antibodies are then transferred into the cell and will somehow end up in the nucleus after some hours. There is another photoactive dye attached to these antibodies, which will then selectively bind to this Ki67 protein, and by irradiating with another wavelength, you then start to generate reactive oxygen, and this will lead to subsequent cell death. So this is a very selective way, because you have to first this selective attachment to this protein in the cell membrane. You really shine your light where you really have to have the action, and then you have the second selection step by binding to this protein in the nucleus. And they are now using this. They want to really target on ovarian cancer to get a therapy for this. So because in usual chemotherapy, you of course would more or less hit every proliferating cell, but they have this nice way of really deciding which cell they want to target. What's also in their field of research is they use gold nanoparticles. They also attach antibodies to these gold nanoparticles, which bind them selectively, for example, here to some lymphoma cells, and if you then irradiate this with pulsed laser light, you get here also a cavitation bubble, and you can decide now if you really use a high pulse energy, you get a strong cavitation bubble, which more or less mechanically kills the cell. If you use less pulse energy, then you maybe also only permeabilize the cell if you want to get, for example, in an application just a substance into the cell which can't enter in another way. But here in this experiment, they really killed the cells. So here is the results of some flow cytometry. So the red cells were the ones where the gold nanoparticles bound to. And if you, after irradiation, you can see here, so this is the dead assay, the dead chromophore, here is the live chromophore. After irradiation, you see here that the red cells are no longer here on this green side, but they were somehow killed. Whereas the green cell, the cells here in the green circle, where no nanoparticles were attached to, they are still alive. So another imaging modality, one of the imaging modalities used in the institute is photoacoustic tomography. So maybe some of you know about this. So you shine also in pulsed laser radiation, which is then absorbed in certain chromophores, so for example here in blood vessels, and due to this pulsed radiation, an acoustic wave is forming, which is then can be detected by when it enters to the surface, usually with ultrasonic transducers, which I think some of you are working on. But this is of course a contact measurement, so the transducer has to be somewhere near the sample, and it usually takes some time to get the data. So in our institute, what we are using now is an optical holographic detection approach. So we also have this nanosecond laser irradiation of the chromophore, somewhere here situated, for example, in tissue. Then the acoustic wave is forming, and what happens is when this wave is reaching the tissue surface, you get here a deformation. And with this holographic detection, you can really get a picture of the surface deformation and then reconstruct where your absorbers have been. This is in principle a very high-speed method to detect this photoacoustic signal, and it's also usable in non-contact mode. For example, if you think, for example, on brain surgery or so, where you might not want to attach an ultrasonic transducer to your sample. Now we come to some examples of what we are doing with regard to smart laser applications. Here you see what I mentioned. If you have, for example, some diabetic retinopathy, the physician, what he's doing is he sets some coagulation points on the retinal pigment epithelium. So he really coagulates more or less the tissue. And what you see here is that sometimes some bleeding can occur. And this is due to the fact that the pigmentation in the retina is really occurring even in one patient by a factor of 2 to 3 on the whole surface. So what he's usually doing is he's setting some test lesions and try to figure out what irradiation parameters to use. But of course, this is not a very good way to do so. If you want to end up with a picture like this, that you have very nice spots in a very controlled way, for example, that you even want to say, okay, I want to have subthreshold lesions, which are not even visible by the eye, or mild or strong ones, then you somehow have to measure what you are doing. And in the group of Ralph Brinkmann, what they are doing is they have here the contact lens, which is put on the eye of the patient anyway, and in this contact lens they have an ultrasonic transducer included. And what they are doing now is they, additional to this coagulation laser, which is usually a CW laser, they apply a pulsed laser with a small pulse energy, which leads to a very tiny temperature increase. And also, like in photoacoustics, you get an acoustic transient, which is measured then here with this ultrasonic transducer. And the amplitude of this signal actually depends on the temperature of the spot which you irradiate. So this is somehow related with the Grün-Eisen coefficient. So if this tissue is warmer here and you start your measurement, then the amplitude of these acoustic signal is bigger. So you have to really calibrate this, but then you can really say, okay, if the signal is as high, then we had an average temperature in this spot, which was X degrees above the starting temperature. And they really now found a way so that you can really say, okay, I want to have a mild lesion or a subthreshold lesion, and then you really, in vivo and during your coagulation, you monitor the temperature and automatically stop the laser before you end up with something like this. This was actually also done with OCT. This is the only example I will show. So we had one setup where you could make this optoacoustic measurement and as well get an OCT signal from the same spot. So this is the spot now on the retina and the pigmental epithelium, and here's now the laser for the coagulation applied. And if you get now the OCT signal, which Helge will explain on later a little bit more, then you see after some time that here the tissue heats up, and due to this heating it will start to move upward, so you see an expansion of the tissue. And if you now measure the phase difference between two consecutive pictures, this tells you how this picture is moving, more or less, to simplify this. And this gives a much clearer signal about what's going on. So you see already here something, but if you now calculate the phase difference in every pixel from picture to picture, then you can get really a huge signal with these phase shifts. And from this phase shift, you can then calculate the length shift of the tissue and get a value for the tissue expansion, which is of course correlated to the temperature, because the temperature increase leads to this expansion. This right? Yeah, you see it's not to this expansion. And if you overlay on the one hand, you see the signal I got with this optoacoustic measurement shown on the last transparency, and if you overlay now this length shift of the tissue, this expansion, you see that they fit quite nicely. So now we come to the more practical side of the work. So in the Medical Laser Center, like I said, we really do some technology transfer into the clinics, and these are two examples. So here you see a clinical prototype for what's called selective retinal therapy laser. So usually, as I said, the coagulation is done with a CW laser, but you can also do this for some diseases in a more intelligent way using microsecond lasers, which lead to less side effects, and you can do this in a more controlled way and get sub 300 newtons. And this laser was developed at the Medical Laser Center, then a clinical prototype was built, which could be used in clinical trials, and finally this led to a commercial product, of course in cooperation with the company who then did the final device development. Another example for this kind of work is we got a thulium laser, a commercial one from IPG, and inserted this in the system, which could really be used in the clinics. And then there were studies performed first on animals, on liver and kidney resection. But finally, this was also done in a collaboration with the company. They then developed a commercial product, which is now available on the market. Also on the OCT side, there is some technology transfer going on. So there's a lot of work on how to put this technology in endoscopic usable probes, so that you can use OCT not only on an open sample, but you can also use it with a minimal invasive surgery, for example. Or there was also a spin-off of the BMO. There's now a company which combines these OCT devices with a surgical microscope, so you can use it also in an operating theater. Last but not least, we have some material processing possibilities. So we have a UV excimer laser station, which you can use to, for example, microhole drilling, or also to selectively ablate thin films. Here you see a retina implant. We got this to remove some polymer film here on the CMOS chip, and we could selectively remove these very thin foils on this implant without damaging it. And to close the circle, I chose on the first transparencies the work Alfred Vogel was doing on these bubble sizes during optical breakdown in dielectric media. And actually, this knowledge is now used in the material processing group because we are using now nanosecond lasers to process, for example, glass. So you can engrave glass, but you can also make structures so that you can break up the glass afterwards easily using this very, let's say, relatively cheap nanosecond laser system. So I hope I gave you a short overview on what we are doing. So we're really focusing mainly on in the biophotonics area, but sometimes we also make some excursions into other fields. And I think Helge can give now a very good introduction on one of the main imaging modalities which is used at the BMO and MLR. So thank you very much.
Thank you. And we will make a question at the end of
maybe so.
the presentation.
And actually I brought some marzipan with me, but I put this behind to the coffee. Or you can get it through.
Should I still wait or? No, it's done. Okay, so thank you for the opportunity to talk here. So this part of the talk will be on holographic optical coherence tomography, which is like optical coherence tomography is a well-established technique now, and we do it in a slightly different way. So that's why we call it holographic. It's the holographic optical coherence tomography. So before I start, I also had some of the Lübek pictures in my presentation, so I'll just show them. So Lübek is located in the north of Germany. It's actually pretty small. So this is the city center here. It's located on a small island. This here is the Baltic Sea, so it's close to the sea. And then there is a bit of the city here, there, but that's really the city center. So this is the campus, which is located right here, so at the southern edge of the city, which has the university hospital here. No, that's the university hospital. The Medical Laser Center and Institute of Biomedical Optics is located here. And here are some buildings of the university. There's another building here now, and there's another building here now. It's rapidly growing right now. Yeah, and this is an image of the institute where we're working in, so that's the Medical Laser Center and the BMO, which is actually, it's grown a lot too, so it's not no more only located here, but it's located in 5 locations on the campus now, so we have like different labs all over the campus, a bit like here maybe. Okay, so, but now to the topic, I'll talk about holographic OCT, and well, before I give a short introduction to OCT, I'll just give a short idea what's the advantage of OCT, of holographic OCT. So in OCT, you usually acquire volumetric images of most of the time of the eye. You can use it in material science too. You can use it on the skin, but the main application is actually in the eye. And the way it works, you can somehow imagine it, it's like ultrasound, but with light. I'll get to it in a minute. And usually what you acquire is like a B-scan, which is like, that's the depth, and that's 1 letter resolution, and you scan the image. And what you can do in holographic OCT now is you can do pretty much everything you can do in holography with it. So you can change the focal location in post-processing. You can apply numerical aberration corrections. So for the eye, for example, there's the problem that the resolution you can image the retina with is limited by the optical properties of the eye. So you don't have like nice optics of microscope objective and so on. You have usually in like your setup, but you have the optics of the eye. And what actually happens there is if you increase the pupil size, the resolution increases until you reach something like 2 millimeters pupil size. And then if you increase the pupil size further, the resolution decreases. It's mainly, well, that's the reason why if people who don't have really good eyes, like make the eye small if they want to see something in the distance, for example. So they decrease the aperture. And if we do it now with holographic OCT, what we can do is we can actually resolve photoreceptors in the retina, which is not possible with like other systems without aberration correction with like a deformable mirror, for example. So, but I want to start with like the basic introduction to OCT. So what is OCT actually? So what we can do with it, I've taught. And there are basically 2 or 3 ways you can do OCT. The first one was time domain OCT. So I'll get to that one in a minute. But in time domain OCT in general, you have an interferometer. So that's true for all OCT applications. So the way it works, you have a light source, which is usually a short coherence light source. In this case, it's an SLD. It's spatially coherent, usually. You then collimate it and split the beam into a reference arm, which is here, and a sample arm, which is here. Now, light in the reference arm is reflected by a mirror, goes back, and goes onto a detector. And light in the sample arm, well, goes into the sample, in this case the eye, say the green path here, goes back, and then is detected by the detector. On the detector, which in this case is just a simple photodiode, you now observe interference between the light of the reference arm and of the sample arm. And if you imagine now a sample which is just like a single layer, if those 2 arms have exactly the same length, you get constructive interference. If they are like different lengths, so if maybe this arm is like half a wavelength longer, then you get destructive interference. And by that, by scanning the reference arm in the length, so you rapidly move it, you can see like the interference modulation there. And this now allows you, so only light from, well, I forgot it, we use a short coherence light source, so only light from one depth really interferes. So you know all the interference you observe comes from the depth, which is like the length of the reference arm. And so what you do is you scan your reference arm, observe this blue interference signal, and the signal you're looking for is this yellow one, which would be the coherence signal in that case. There's another way to do it, which was published like maybe 15 years ago now, which is Fourier domain OCT, which just is pretty much the same, just that you don't move your reference arm anymore, but use a spectrometer as a detector. And the way this works now is if you have a sample in one length, you get destructive and constructive interference for different wavelengths. You can imagine it slightly, well, a bit like a laser resonator. So for like some wavelengths, it's constructive interference. For other wavelengths, it's destructive interference. If we now have another sample in another depth, it's like a longer resonator, so you have more modes in the resonator, so the interference signal has a higher frequency. Now, usually we don't have just one of those samples, but we have both, so we get a combined signal, which is like the combination of both. And the way we can reconstruct those two depths now from this is just applying a Fourier transform on that, because the frequency here is directly related to the depth here, so we get the signal for the first depth and for the second depth. And that's the way how you can do it with a spectrometer. The advantage of this technique is that we don't have to scan your mirror anymore, and it's faster, it has a higher sensitivity, but you somehow have to build a spectrometer, which can be done by using maybe a grating and a camera, or a photodiode and a tunable light source. You can imagine, well, you change the wavelength of your light source one after another, and then you can use a photodiode here again. So that's the basic principle of OCT. So the top row now is Fourier domain OCT. So basically now, if we have done this, and we have measured a single axial profile. Now if we actually want to acquire images, we somehow need to scan the sample. So people just scan this beam across the volume, and then in the second dimension, and then actually get a 3D volume. Another way to do it is to, in the case, to somehow parallelize it, so we can use a 2D camera instead of a line camera and sample the second dimension, or we can actually use a tunable light source and an area camera to actually get like the two lateral dimensions on the camera and then the different wavelengths over time. The same is true for time domain OCT. So there you can imagine or image just like one single depth. You can scan that in depth. You can do it with a line camera, then you get like a single line, and you can do it with an area camera where you get like a full plane. Well, I'll focus in this talk on the full field systems because they have the advantage that which is crucial for the holographic OCT, that there's no sample motion between the acquisition of different lateral points. I'll get to that in a minute. Now I'll start with the time domain way of doing it, so with the en face full field OCT. So what we acquire in OCT, usually we get the amplitude and we get the phase information too. So the phase information actually allows us to reconstruct or to do what Birgit told, just to see like the expansion of tissue of really small motion, because it's in the nanometer regime, or to actually do things like refocusing and so on. The problem there is that if we have a living sample, the phase relation between neighboring lateral positions isn't really, or it's pretty much random because the sample moves in between, and as we're sensitive to nanometers, the lateral phase relation is really made by the motion of the sample. And that's why we tried to do it with a parallel approach, so we wanted to acquire all lateral points at the same time. So this is the way we did it, or one idea is that's called full field OCT. We have our light source again, as a superluminescent diode in this case. We split it in the reference and the sample arm. We illuminate the sample aerially and then image each point of the sample onto the camera, where the light interferes with the light from the reference arm. Now the problem is that we still don't know this. If we look at the signal here on the camera, we still don't know if it's just interference what we measure, or if it's just different absorptions or scattering coefficients of the sample. So we still need to sample light at a few different lengths of the reference arm. So we actually would have to move that one still. Now we don't use a photodiode, but a camera, and the camera is usually way slower than a photodiode. And as I said, we have problems with sample motion, so we somehow have to measure different depths of the sample of the mirror here, or different phases within a single shot of the camera. And the way we did that is, so that's on the right is just now a sample which is across. First, we needed to get some space on our detector, so we added an aperture or an iris here. So now multiple points of the sample here, or one point of the sample is sampled by multiple pixels of the camera. And now we can use them somehow. And what we did is we just tilted the reference arm slightly, so the phase between, so the reference arm is shorter here and longer here, so we have a phase shift between neighboring pixels. And from that, we can reconstruct or we can discriminate between the interference and just different sample scattering coefficients. Well, this is pretty much how it looks in reality. So what's hard to see here, you get the interference, and that's just the en face image. What we do now, and we acquire one image for different depths. So we still move the mirror in the reference arm to get a different depth, but for a single depth, we just need to take one image. We now Fourier transform it, and there you see nicely separated the interference term here, which is the cross-correlation term, and everything else, so autocorrelation, the reference light, all the light which doesn't interfere, is in the center. So to reconstruct the image now, we select just one of those terms here, and then to get the interference signal there, we would just inverse Fourier transform it. What we can now do in this Fourier transform is the pupil area, so we can apply a different phase here. So, for example, a defocus is a different phase in the Fourier plane of the image. So now we can pretty much, in post-processing, change the optics we used. So we can simulate a deformable mirror here. We can just change the focal length or the focus of the sample, and that's really powerful. So what we do after applying this phase correction, we just inverse Fourier transform it and get our fast image, and we now look at it from a different perspective. We can just render a volume out of it, something like that. Well, the setup we used looks a bit different, but not much. It's pretty much the same. So the only problem was that since we tilted the reference arm, the reference light didn't anymore hit the camera, but went here. So we changed it to a Mach-Zehnder interferometer. Well, we changed it back now, but that's the setup we fired our images through. So the specs, I think they aren't that interesting. I just go over it. So that's now images we acquired with it. So this is the original image. It's like of a really myopic eye. It's 5 diopters myopic. And it's an area, so it's in vivo. It's one of our students. And that's an area close to the optic nerve head. What you see as well, you have nicely discriminated different depths here, but the label resolution is really bad because, well, it's a myopic eye. What we can do now is we can apply our defocus compensation in post-processing. So that's the exact same data set, just with a numerically changed focus, like in holography where you can do it. Well, and yeah, we always acquire a whole volume, so we just scan through it. The acquisition of this volume takes about a second. And in that setup, there's, besides the motor for the mirror, which is right now expensive, there's nothing really expensive in it. So there's a USB 3 camera, there's a $300 light source. That's really simple. Well, now there's one problem if we want to really correct for higher order aberrations, and that's to understand that we can have a close look at the camera. So in green we have the light coming from the sample for just one point, and that's the reference light here, the blue. And those are individual pixels. Now our modulation frequency, or the carrier frequency, which shifts our interference signal in the Fourier domain out of the central and allows us to discriminate it, is actually determined with this angle. So, for example, this would be constructive interference here. The reference light travels a bit further, so that might be destructive interference. But now, this frequency which we get out of it is wavelength dependent. So for a red wavelength, for example, we get this frequency. For another wavelength, we get another frequency. And as we acquire or image all of them at the same time, we get our information of the sample, which is like here, encoded at different spaces in the frequency domain, and they all overlap. This doesn't do any harm if we don't manipulate the phase somehow, but we want to do it because we want to get rid of all this stupid aberrations. So the way we resolve this is, well, it's pretty much known from holography, but not for this purpose. We added a grading here. So, and now for the grading, the angle of the diffraction is dependent to the wavelength too. And that cancels out with the angle here. So we actually have them nicely overlapping now. And with that, we were now able to acquire or to apply numerical aberration correction on the images. We use an iterative approach for that. We used for other techniques before. We used a pupil size of 6 millimeters, so we dilated the eye, and then I measured it with a numerical aperture of 0.18. And the resulting image, this is V-scan again, looks like this now. What you can see here, if we closely look, is some really high, some nice signal in the RPE here. So there's, in traditional OCT images, there's not much lateral structure here. In this one, you can now see it. Well, this is like the video, because we also acquire videos. And now if we just look at this layer and look at the more fast image of it, so just look in this plane, you can see the photoreceptors here, which aren't visible in common OCT approaches. If we look at the same image before aberration correction, you pretty much see nothing. Now, what you can imagine see two here, you just see the photoreceptors in the center. You don't see them here, you don't see them here. And this is the case because the aberrations of the eye aren't like spatially constant. So for this section of the eye, we have different aberrations for the center than for that side. So what we can do now is we can optimize our images for like another area and get the photoreceptors here, or we can optimize it for that area and get them there, and then we can just fuse them together and get like the photoreceptors from every place there. Okay, so that's how we use the lateral phase stability in holographic OCT. Now for like effects, so that's just one thing to that topic too. We had it in a lab setup first, and now changed it to like a handheld device. So we were trying to make a really cheap OCT, which can be used in the clinic. So right now it's a really compact system which can be used handheld and actually works quite well. Yeah, so until now we had just the phase stability in this plane here. And if we want to look at phase changes in the axial direction, we can't really do it because the phase is just, well, determined for this area. And if we then move our reference position to another depth, we get a new phase. So what I want to talk now is about Fourier for the domain full field OCT, which was actually done before by our group before the fast full field OCT, but it's really expensive. So we started with the other one too. And what you get here, you pretty much get the whole volume in more or less a single shot. I'll get to it in a minute. So what we did here is, the setup is pretty similar. The only thing we did is we exchanged our SLD with a tunable light source. So now over the time we have different wavelength of the light source and then acquire one image with a camera for each of that. The problem now is, again, motion. So the sample moves, and we somehow want to acquire it pretty much in a single shot. So we need a really high-speed camera, which is a major drawback here. So the camera we used is able to acquire 60,000 images per second at a resolution of 800 or 900 times 360 pixels, I think, which allows to acquire 117 volumes if we decide to have like 512 wavelengths, which results in 256 depths. We can also reduce the images we acquire per volume and then get higher volume rates. Well, you can imagine these cameras are really expensive, so that one is about $100,000, so that's far away from being used anywhere else, it's just lab equipment. However, what we can do with it, let's skip that, is we can pretty much acquire the same images as before, just a lot faster, and we now have a distinct phase relation in that direction too. And we can use that now, for example, to image like dynamics in the eye. And the first one I want to talk about is pulsation in the retinal vessels. So with each heartbeat, blood is flowing through the vessels, and the vessels expand here. And now we have vessels in the upper layers of the eye, so here, and you have a lot of vessels below, so like closer to the brain of the eye, and they all like overlap. What we wanted to image now is the pulsation of those vessels in the eye. And the way we did it is we looked at well, we acquired images and always made a phase difference. So we looked at the phase at this place or at that layer, and at the phase at that layer. And for volumes, one volume after another, we always calculated the difference between those. So the phase from this layer in one volume, and then the next one we calculated the difference. The same we did for that one. and then just showed that. And what you can see now is that the retina expands there. So this is an artery and that's a vein. And if you look at it closely, that you see that they somehow behave slightly different. So you see some kind of double pulse here and then a really slower pulse here. That one starts a bit earlier than that one. So that's really interesting. If we look at that in a graph, so this is the expansion over the time. You can see it for the artery, the vein. So for the artery, you get this pulse. Sorry. Yeah, that's the one for the artery. This is the one for the vein, which is just a lot smoother. If you see them both, you see that there's a delay between those two. Until now, there's no other way to somehow image it, because you need the phase information in Z, and it needs to be really fast. Another application where we did it that's related to the thing Birgit talked like a couple of minutes ago is photocoagulation. So what you can do in OCT, or with any OCT device, you can look at the phase difference at a single point. You get the different layers. If you shine in with a laser onto the eye, you see that this expands here, and you measure that expansion. After a while, it looks like this, which is pretty much scar tissue here. And we wanted to know if we can somehow visualize it. Birgit already told it, yes you can. And you get something like this. But with the way Birgit told, you can only see the expansion in the axial direction, so just in this direction. What we still don't know, well, the tissue also expands in other directions, but there's no way to tell how it does it if we just look from above. So we somehow need to look from the sides. And there's actually, if there is like lateral movement, it might be seen as axial movement, so there's a lot of difficulties here. And the reason why this is the case, so if we have a movement of something here, going in that direction, and look from above, we just see like this component of it. If we have a movement, if we now look from different sides, so from this side, the movement in this direction looks like this, so a lot smaller. If we look from the correct side, we see like the actual movement. So what we want to do is actually we want to look at we want to see this phase shifts or phase changes from different directions. And well, one nice thing is we can actually do it because we have this lateral phase stability. So this here is actually the aperture we acquired. So the whole one here, I'm sorry that's in German. But now we can virtually select just subapertures for it. And like the subapertures now relate to different like angles where we're looking at. So we can now look from here, from there, in that case. And from that we can calculate the motion in the lateral dimensions too. So we can actually really determine the motion. We did that in phantoms. Here you see, well, that's pretty much what Birgit showed before. You see the translation and the local expansion, but which nicely correlates to like the power we put in there. But we can also now look at the lateral movement, and we see that there is in x direction there's a movement to this side and to that side. That's important. It's called here, and in the y direction in that side and that side. We can now combine it and see that there is like actually no motion in the center where we focus the laser, which actually makes sense. So that doesn't go to the side. And then if we go a bit further away, we have motion to like the centers. Oh well, that's just the amplitude of the motion, and the direction is nicely, well, it goes away from the center. And that's something you weren't able to see before. Again. Now there's another application, so we wanted to see or look at this small motion, and now we want to look at single photoreceptors. And we wanted to look at the response of single photoreceptors to a light stimulus. So we don't want to coagulate the whole retina now, but just use light as we would see it usually in a healthy eye. So we added a projector to that setup, and we just project some pattern into the eye. And then we looked at the difference, or the phase difference between those two layers here, which is the outer segment tips and the inner segment tips of the photoreceptors. So the photoreceptors go from here to there, so they're pretty long. We just wanted to look if they elongate somehow. And well, yes, they do. So they elongate with a stimulus which is not really thermal. So that's the physiological response of the photoreceptors now. So that's the initial image. This is slightly after the stimulus. And now you see that there's some motion, and after a while you actually see the pattern we projected in there, which is like 4 boxes here, and there's another 4 boxes here, and there's 1 box in the center. And you can actually find this pattern again. The signal is highly reproducible. So actually first, the photoreceptors get a bit smaller, and then they increase in size. We did it for like a lot of measurements in different eyes, and it's always the same. So always see the small dip and then the expansion afterwards. And after a while, over a couple of seconds, this signal completely goes back. So if you look at it for a while, yeah, you have the initial state again. What we can do now is we can combine this with the aberration correction I taught in the beginning. So we can now look at this for single photoreceptors. So here you see the pattern again, so the whole image. And if we just look at this small portion now, you can see that like pretty much most of the photoreceptors expanded, but those 3 here and that one did not expand somehow. We did this measurement 10 minutes later again and saw that the same 3 photoreceptors did not expand. So something is going on with those photoreceptors. I don't know what it is, but there might be actually some value in those data where you can actually, well, I don't know if it's associated with like the renewal of photoreceptors, if it's might be associated with diseases. It's pretty early stage still, so we didn't know yet. Yeah, so that brings me to the end of my talk. So holographic OCT can be either used for building a really low-cost OCT system, which was the first part, or we can go to the other side and build a really expensive setup, which is then ultra-fast, so it's actually the fastest OCT system you can build right now, and which allows for phase-stable volumetric images for imaging. And that then allows for numerical aberration correction. Okay, that can be done with a really cheap one too. It allows for 3-dimensional measurement of nanoscale motion, which can be this pulsation of the retina. It can be the expansion of the photoreceptors. It can be a lot more we don't know yet. And it allows to see the motion from like all natural dimensions if we use the separature approach. Yeah, and I think that's already the end of the talk. There's a couple of publications which relate to all of those applications or setups here. With that, I'm at the end of my talk. Thank you for your attention.
Thank you very much. We have time for questions. Do you have questions? No question? I have one for you. How do you get only one cavitation bubble? Because if you shut nanosecond pulses in the water, you will have not around somewhere.
All I know is that they really strongly focused it. And I think they have a 40 so a microscope objective really strongly focusing this. And then they have a high-speed camera, put in another laser to illuminate this.
Yeah, the shadow graph.
Yeah, exactly. And then they were never talking about all this one cavitation bubble.
I think they actually look at how they have to shape this bubble. So, for example, if you put a plasma there and then use a second pulse, you can manipulate the bubbles to build some jets and so on.
Unless I have a one impurity there, and I can get around kind of thinking about it. But
Yeah,
I think they have the
I-
energies really to get one. I would assume that they get one, but I will check this. And I know that they also built now an interferometric setup to really measure the interference from the front surface and back surface to get more information on these bubble dynamics. But
I will focus with better mind.
but we will check. Maybe they have more and never talked about it. So.
Well, they worked on that for a long time. So Alfred Vogel actually does that work.
Yeah.
So he does that for like, I guess, I would have to lie, but I would guess 20 years now.
For Helge, so to understand a bit better this OCT technology, like these images you're showing us, we consider them as maps of the scattering power of the tissue or of the absorption coefficient of the tissue.
So what you measure in OCT is the backscattering. It's a map of scattering, of backscattering. Yeah, so it's the scattered light which goes back into the aperture.
If you would like to measure, for instance, the refractive index with OCT of inside the eye, is that easy to do?
I don't think so. Or I don't know how to do it actually. I think there was some work on it where people tried to do it, but well, you can do it if you have something next to it. So if you have like the comparison, if you know the size of it, and you have like depth, or you have like air for comparison for a microscope slide, that's easy, but it doesn't really work for like in living tissue. So you can imagine you have like there.
Yeah.
If you have like something here, which might be a mirror, then put something here, and you image this whole thing. This one would actually look bigger in the OCT due to the refractive index. So for that, you could imagine or image that, but I think in living tissue it's fine.
And you mentioned about some applications on skin of OCT. Like what would that be? What are you measuring there? Or
Well, you can actually see like the different layers there. You can see the sweat glands in the tissue. The idea there was to actually discriminate between tumors and healthy tissue, which wasn't really or isn't really used because the burden there isn't too big. You just cut it out and put it into histology anyways. So there are actually I think one or two commercial systems which work on skin, but the main application is still in the eye. So for the eye, well, for obvious reasons, you don't want to cut anything out of the eye. You can't look at it from different angles at the retina. So and if you have like changes in the structure there, you often can't see it with a fundus photography anymore. So for example, there are like diseases which change the layers in the eye, which you don't see in the projection, but you see in OCT, and there's just no other way to do it right now. Ultrasound doesn't work because you need contact and you have to penetrate through the whole eye to get to the retina, so you have to penetrate like 2 centimeters of eye to get like the layers there, which doesn't really, well, it should work, but the resolution is really low and you don't want to have contact with the eye. You can avoid it somehow.
Okay, see.
Are you doing the in vivo images in humans?
We're doing it
In humans? It's complicated to get permission to do it.
well, it's actually not complicated at all if you do it on yourself.
To sign your permission.
What we do, we always have to do the data safety, but the power we use is pretty low. So OCT is like, if you have a scanning OCT system, it's below 1 milliwatt. Below, it's like 800 microwatts, so that's safe. So that's why you can just do it. We right now have, for this low-cost OCT, we have a study in the clinic, so for that we have to go through all this process, which takes forever. But yeah, that's in the clinic now and there, like first results now. So we just started this week, on Tuesday, so but it's going on now. Yeah, it's usually a lot easier to do it on humans than on animals as well. You can tell, like, if I look at it, I know, well, I have to look at that direction. It works. You can't do it with them.
Thanks.
Have more questions?
Sorry, I came a little bit late. I didn't see what kind of laser are you using. Is it pulse laser or femtosecond?
No, so for the time domain OCT system, we are using an SLD, so a superluminescent diode, which is like a hybrid between a laser and an SLD. So it's pretty much a laser without a resonator. So it has it's laterally coherent but spatially incoherent. So they have a bandwidth of 20 nanometers to 100 nanometers, but are spatially coherent. They're pretty cheap. So if you buy a free space one, it's like a diode. If you buy a single one, it's like $300, something like that. But it's far away from a laser. For the tunable light sources, we wanted a really slow one, and that's basically just a really slow tunable laser. I don't actually know what it is exactly. For OCT in general, so if you don't use this full field technique, but the scanning technique, the challenge is to get the tunable light source really fast. So you want to tune the whole wavelength range really fast. And for that, there are like different lasers. There are 3D domain mode lock laser, which like built a couple kilometer resonator in fiber to get it really fast, so they don't have to build up the so they don't have to wait for the laser to lace for every wavelength again. So they have a buffer for all the wavelengths, pretty much, and just amplify them. There are pixel light sources now which are used, but here we use the really slow one, which is a really made. It's not in femtosecond. It's pretty daily.
Your OCT systems are commercial or prototypes?
All of those are commercial. So the full field OCT system.
How much cost compared to the
commercial?
Yeah.
So the lowest one right now in components is about $8,000. 8,000, where 4,000 are the motor right now. So there's a motor in it which moves the reference arm between the acquired images. And since we wanted to do this whole thing pretty fast, we wanted to have a start-stop movement of the whole thing. So we wanted to move 7 micrometers and then need to have the mirror standing there. We just give it 5 milliseconds for that. So that's why, we took the first motor which worked, which was from PI stage. PI is a German company which is pretty expensive. But that worked, and we didn't think about that for the first time. We are looking now into different approaches for that. So one way which we are pretty close to actually get that performance is just a step motor, which is really cheap then again, and there are other ways to do it. Other than that, the cost is the camera is about $600 right now, the one we use. The SLD is $300. We use a laser diode driver, which isn't expensive if you buy a small one. And then there's just the beam splitter, the lens, and the prism. That's all, which is pretty much in there. There's a $100 rating in it right now. So that's going to be really cheap. The other one is $150,000 to $200,000 components right now.
Yeah.
Have you developed a specific chemical method to beam or link the nanoparticles with antibodies?
Yeah, probably we do have, unfortunately. I can't tell that much about it, but we could maybe exchange email addresses, and I can contact you to our biologist who can really give deeper insight into this topic than me. So, yeah, so maybe we can exchange addresses.
More question? If not, we want to thank again for the seminar, for the journalists.